A 7 billion parameter AI model has around 7 billion learned numbers. So when people say the model runs on a GPU, where does it actually live? Is it inside the GPU cores, inside the tensor cores, inside the cache? Well, not exactly. The wrong image is that the model is sitting inside the chip like software inside a box. But that's not how it works. We can depict the real picture like this. The model mostly lives in GPU memory, and the chip streams pieces of it through the compute pipeline as fast as possible. Let's break it down. First, an AI model is mostly learned parameters. These are the numbers the model learned during the training. So kind of small knobs to tune the model to give you the output which reduces the error. Most of them are weights. For example, when you download the open source model, you are mostly downloading these numbers. When you download a 7B model, it has around 7 billion learned parameters. If each parameter is stored in floating point 16 or brain floating point 16, that is 2 bytes per parameter. So the rough memory math is simple. 7 billion parameters times 2 bytes is about 14 gigabytes. That means just the model itself needed around 14 gigabytes of memory in floating point 16 or brain floating point 16. And you need to pay attention that we are not counting activations or KV cache or runtime overhead in our simple calculation. It's just the parameters, basically the model itself. This is why memory capacity matters so much. If your GPU has around 8 GB of VRAM, a 14 GB model does not simply fit in full precision. You need a smaller model, or you can do offloading or quantization. But this creates a misleading picture. Even if the model fits in the memory, that doesn't mean the GPU can use it efficiently, because fitting is only the first problem. The second problem is the movement. For example, during inference, the GPU does not load the entire model into the compute units at once. That would be impossible. Instead, the parameters sit in GPU memory and the hardware reads chunks of them layer by layer. The compute unit work on small tiles of data. Those tiles move from GPU memory into cache, then into faster on-chip storage, then into registers where the actual computation happens. Think of it like a kitchen. The GPU cores are chefs. GPU memory is pantry. The ingredients are not all in the chef's hand at once. They are brought from the pantry, prepared in small batches, used and then replaced by the next batch. If chefs are fast but the ingredients arrive slowly, the kitchen waits. That's exactly what can happen in AI hardware. The tensor cores may be extremely fast, but if memory cannot feed them quickly enough, performance drops. This is why memory bandwidth is so important. High-end AI accelerators, they use HBM because they need to move huge amount of data every second. This is also why quantization matters. If the same parameters use fewer bits, more of the model fits into the memory and less data has to be moved across the memory bus. So quantization is not only about saving space, it also reduces memory pressure. But now comes the part people usually forget. The model is not the only thing taking the memory as we said during our calculation. For example, do you remember I mentioned activations? Activations are temporary working values created as the input passes through the model. During inference, many activation buffers can be reused layer by layer, but they still require memory, especially with large batches or long prompts. And for language models, there is another major memory block, the KV cache. When a transformer generates text, it doesn't want to recompute the entire conversation from scratch for every new token. So it stores keys and values from previous token. That's the KV cache. It's more complex process, but the definition is as simple as that. The longer the context, the larger KV cache becomes. This is why a model that fits with a short prompt may run out of memory with long conversation. The parameters are fixed, but the KV cache grows as the context grows. There's also an important difference between prefill and decode. Prefill is when the model processes the initial prompt. That stage is highly parallel and can often use the GPU compute units efficiently. Decode is when the model generates one token at a time. Especially for small batches, decode often becomes memory bound because the GPU repeatedly moves weights and KV cache data to produce each next token. So when someone says this model fits on a GPU, they do not only mean the weight file fits. They mean that the parameters, activations, KV cache, and runtime overhead, all of them fit. And the memory system can fit the compute units fast enough. So the final mental model is this. GPU memory stores the model, caches stage pieces of it, registers feed the computation, the cores do the math, the memory system keeps everything moving. An AI model does not live inside the GPU cores. It lives mostly in GPU memory. And modern AI performance depends on how efficiently the chip can move that model through through the machine. Until the next video, good morning, good afternoon, and good evening. Bye.